So welcome to the fourth talk of the third day of UGM 2021. This is Radha Konduri and Dmitry or Dima Khavich from BMS, from Bristol Squibb, and they're going to talk about leveraging iRODS for scientific applications in the Amazon cloud. There you go, Radha.
Yeah, hello, greetings everyone. I am Radha Konduri. I work in Bristol Squibb as Digital Capability Manager for Research and Development Data Management Platforms. BMS is a leading biopharma developing innovative medicines in oncology, fibrosis, cardiology, and cell therapy. My team provides IT support to research and development teams by providing infrastructure on-prem and on cloud, along with data stores and cloud computing for R&D applications. I am accompanied here by my teammate Dmitry Khavich.
Hi everyone, my name is Dmitry Khavich. I am a systems engineer and iRODS core team engineer here at Bristol Squibb, and we will present our project today as a team.
So today we are extremely happy to present to you two projects that has helped us leverage iRODS for scientific applications in Amazon cloud. These projects have made a significant impact on the work that our scientists do. It is all about data. BMS has very large scientific data that is generated in labs, and this clinical data is growing fast at an exponential pace. Today we have tens of petabytes of data that comes in different forms and from different data sources. With this kind of volume, we constantly face challenges for processing, visualization, and analysis of these data sets. What I've highlighted here is the kind of data that we are focused on in the two applications that we are presenting to you today. Our research and development teams are at different locations. Their labs have various instruments and data sources that generate data in a variety of formats. Much of this data is instrument-generated images, and the metadata on these images is essential to understand what kind of data it is and to conduct the analysis. This slide represents lab data challenges that we see on a daily basis. As you can see here, the data accessibility and sharing becomes difficult when image acquisition systems are local and siloed between teams. Replication is a foundational concept in science, but this doesn't always happen. And data insights are only as good as the data that drives them. Data mining becomes difficult due to the lack of good metadata annotation, and image data sets are hard to find, difficult to extract. Data is not actionable, meaning the scientists find it hard to search the data, transfer the data, or even convert the files to different formats. This slide shows the solution that we proposed and adopted to resolve most of the lab data challenges that we face. This is a typical workflow for many BMS pipelines. The data generated by scientific lab instruments is stored in a local NAS storage. This data is then transferred to the S3 buckets using different modes like the storage gateway, data sync, or Amazon CLI commands, or even Snowflake. A 10 GB per second direct connect makes this data transfer fast and efficient. Once the data lands in the bucket, we have the iRODS system that scans this bucket, ingests the files, and then tags them. And finally, the UI applications enable the users to search for the files, request for the data using iRODS metadata catalog. In the next slides, Dima will explain how we implemented this pipeline for our one project called Lab Data Management. Over to you, Dima.
So our first project is lab data management for immune oncology. As you may or may not know, immune oncology field is mostly interested in the T cells. What are T cells for the non-bio people? T cells are the part of the immune system that focuses on specific foreign particles rather than generically attack any antigens. T cells circulate until they encounter their specific antigen, and as such, T cells play a critical role in our immunity. So researchers in the immune oncology field interested in the chimeric antigen receptor, CAR, and T cell receptor, TCR. Our project combines from three major components: lab data hub, data model, basically tagging and describing, and discovery workbench, which is an analysis tool. It's a third-party tool. In the next slide, I would like to start my description from the end user, the scientist in the middle. Here her preparing experiment using the instruments and lab tools. So acquired raw data or raw images being generated and then being transferred into the drive or storage. Amazon Storage Gateway sits and listens to this drive, new arrivals, and sends files or objects to AWS S3 bucket. When data lands into S3, Amazon Lambda is being triggered and starting ingesting or registering objects into the iRODS catalog. Then rule engine driven tagging process happens at this point. File path being updated into a tool for research and analysis. This is a third-party tool out of the scope of our presentation. Annotating and tagging data elements and informing end user happens. And back to the user, user have ability to access new processed experiment data. After initial ingest happened, tagging process being triggered by rule engine rules. Radha will elaborate it in details later. Also, we have separate cron job that is running every hour in any given period of time in order to create special integration file in comma separated value format. Then this file being transferred to the third-party tool for further processing. Next.
Okay, here I just wanted to talk a little bit about how our iRODS provides flexibility to extract metadata from different sources simply using code and iRODS client API. We are able to extract the metadata values just from the file path of the file that's in the bucket using regular expressions. We are also able to parse the AWS S3 head object response to extract the time of creation or size of the file. We aren't using the checksum that think that's available in iRODS, but we do create a unique value for each file by using the Python hash library for the contents of the file. And then we have the different schemas that are defined in XML, JSON, or a CSV or a text file. Simply, we read that those files and then set the metadata on the data objects or collections.
Second half of this slide represent some details of the special integration file. Every hour we run integration script via cron tab that performs scanning of all object landed into the collection in the last hour, then selects those that meet specific criteria, specific tags, and only those specific objects are listed together with their tags of interest, sorted, grouped, and final comma separated value file being generated, then copied over to a specific S3 location, from which it being picked up by the third-party research and analysis tool. So here I'd like to list a couple of challenges that we met. We had initially one big SQS for all our projects that hosted in one zone, but we were unable to purge stuck messages without being purging good messages from another project. So we separated our SQS queue by project and also by environment. In the comma separated value file generation, we overcame special characters in the file names, such as quotes, percentages, and such, and especially commas, of course. And also the limit of the iQuest command for arguments. If we had more than 3,000 objects landed within last hour, we had to split it into 3,000 chunks to handle it better. Also, worth noticing performance issues that we overcome by bumping compute power of EC2 instance, increasing maximum number of concurrent rule engine server processes accordingly. Currently we have 16, and all these 16 virtual CPUs of our machine are utilized. And also we optimized Python code to tag empty files. So in conclusion, I would like to say that this project was very interesting for us and challenging to work on. And we took it as our baseline, and we built on top of it our next project named Discovery Imaging Platform, which Radha will describe next. Over to you, Radha.
Yeah, so the second project we would like to showcase is our Discovery Imaging Platform. And here is the problem statement. Advanced digital microscopes generate massive volumes of images, including 3D images and time series data. But analysis of these complicated image features is a great challenge for our biologists. They need to quantify biological characteristics such as cell count, a biomarker, or calculate metrics such as drug occupancy. And this has driven a need to seamlessly and automatically ingest, annotate, share, archive, and analyze these image data sets. So we proposed this solution that I'm describing in this slide. We propose that the image data sets from the instruments be automatically validated and ingested into iRODS. We implement a rules engine logic to tag these data set with meaningful metadata. Then there is a need to develop an interface, a user-friendly interface to provide intelligent Google-like search operations on these images. And finally, we integrate with vendor SaaS, software as a service, to perform image format conversions, which is required by many external image analysis platforms. This slide represents a very high level architecture of our project. As you can see, we've divided into 4 different categories, which are the image acquisition layer, the image management layer, image analysis layer, and results and reporting. I will explain more about this in my next slide, which is pretty much the same. So here we have the high level flow of the data that moves all the way from the images to the image analysis platform. Originally, the scientists would connect to the instruments through instrument PC and perform their analysis or actions on the data manually, which was time consuming. This was also a siloed channel, as they could not share the data to their peers in other locations. Finding the data set of interest also was a challenge. But now this data is automatically validated as the data comes in. We're using code on these servers. And then it is moved automatically to the S3 bucket through a storage gateway, because there are some cron jobs that run on this server, and they periodically push the data into the S3 bucket. Once the data moves into the S3 bucket, the SQS queue receives some messages which are listened by Lambda function, and the Lambda function then ingest the data, and they tag the data in the iRODS metadata catalog. And then we also developed a UI interface developed in ext-sencha.js. It queries this iRODS metadata catalog through an Amazon API gateway, and we have a REST web service written in Python, which queries the data and sends the response back to the UI. Then the users are able to analyze the data using different tools. The users are also able to transfer the data from this bucket to a vendor bucket, where we have vendor services that convert the files into different formats. and then all the files are brought back to the original bucket, and they are again tagged. All of this happens automatically, but we track the process, and we also notify the users if anything goes wrong. So everything is being tracked. I would also like to talk about the high level of the data model that we created to drive the file tagging process. We categorize the data into 4 different types based on whether the files are raw images from the instruments or converted files, like the stitched or converted files from vendor SaaS. The tagging process begins as soon as the tagging details file, as you can see here, lands in the S3 bucket. The file register event fires up the rule-based engine, and a PEP function is added. PEP function adds the task to the delay queue. When the task runs, the iRODS reads the schema in these XML or JSON or CSV files, and then tags the data or collections with the metadata. This application is very complex. It's innovative and one of its kind because it uses some cutting edge technologies. We have had many challenges to make it seamless from users' perspective, but I would like to talk about a few challenges that we came across with metadata cataloging in specific and performance when querying iRODS. So initially, our data model was to simply tag the files only, but we soon realized that the querying the iRODS for specific types of files was becoming slow as the count of files increased in iRODS. The time to query 200 specific images in iRODS when it had only 30,000 files was taking about 25 seconds. So we needed to optimize this. So we decided to tag the collection also. So as you can see here, the tags that are common to all the files is now attached to the collection itself. So querying for 200 specific images is now a 2-step query. First, to query the collection of interest. And once we have the query, we would simply do a pagination display of the files. So to query the collections of interest, when we had 3,500 collections is about 12 seconds. And then a pagination view of these files takes about 8 seconds. Now we have a lot more collections. I think we have more than 4,000 collections and millions of objects, yet we are still able to optimize this query. The other performance challenge that we saw was loading the search UI form with existing and latest values. The time to query for 6 unique attributes, the unique values of 6 attributes from iRODS took about 24 seconds. So we decided to use a DynamoDB to store the values. Now the search portal, it queries the DynamoDB through an Amazon API gateway and a Lambda function, and receives the response back in less than 1 second. The way we've maintained the latest and greatest data in DynamoDB is through a cron job. I have a cron job that runs periodically. It triggers a Lambda function that queries the iRODS for the data that we're looking for, and then it puts the data into the DynamoDB table. So we always have the updated values in the DynamoDB rather than the old approach, which was causing a performance issue. This last slide for this project is how we optimized a performance issue nearly 3,000 times. The users sometimes need to update metadata of files in a collection. As you can see here in the metrics, the time to update 25 attributes for 6 files took about 50 minutes. This clearly was extremely slow because of the nature of the MSI mod AVU metadata function, because it sets only one AVU for a data type or collection per transaction. But now the iRODS client API has another atomic function that does the operations for a batch add or remove per transaction. So we were able to optimize and save the same 25 attributes for 6 files in about 1.12 seconds. So this was improved 3,000 times. And needless to say, it made the developers happy, it made the users happy, and we are able to achieve our goals. So this project was really interesting for us. It was one of a kind and a new one that we had never done before. So I'm glad we pushed it so far, and we've recently delivered this project, and we made the users very happy.
I would like to talk a bit about the ingest process we used in both of our projects. Old architecture or old approach was initial ingest using the ingest tool and workers combinations plus cron tab-driven scripts to ingest on a regular basis. So downsides of this approach of using the ingest tool plugin would be the iRODS catalog is always behind, and deleted files are not taken in the account, they just stay in the catalog. So we constantly felt the need of the near real-time ingest implementation, and with the great help of iRODS consortium, we moved to the AWS Lambda solution. So here is the very general overview of our ingest Lambda client for iRODS. As you can see, the instruments producing files or images that are stored into AWS S3 bucket. Bucket event triggers on the object create or object delete generates the SNS or SQS messages, and AWS Lambda listens to those messages and triggers and performs registering or unregistering the object in the iRODS catalog. So this slide represents that we had to make our single Lambda that handles same iRODS zone to handle multiple projects. By creating multiple triggers, all of them SQS type, we now have more controllable ingest solution with one single Lambda. And here are some notable technical and configuration details of our Lambda function. Worth mention that, again, with the great support of iRODS consortium, current version of Lambda can handle Amazon multi-part object create and also learn how to handle observed errors. And at the bottom, you see a GitHub repository location of this Lambda function. Some more configuration details listed here as well. I will let you stare at this slide for a couple more seconds, and let's move on. So in the conclusion, I would like to say that using iRODS at BMS helps managing more than 10 petabytes of data in more than 800 million of files that located on distributed resources, such as more than 200 S3 buckets or multiple NFS shares. We are looking forward to use iRODS innovations such as new metalinks browsing capabilities, maybe Kanki, Yoda, and NFS rods. So this slide represents our future organizational approach that we are planning to implement. In the current state, we have one production zone, which hosts multiple projects that obviously started to fight for the resources, creating bottlenecks such as SQS queue that we solved by splitting compute power, database requests. This is not yet solved. So in our plans is to separate projects in a manner of one project, one zone, but then create federations so the scientists from different labs or divisions or regions or geozones could reach out and access data across the project. So federation will solve this, and we're going to be in accordance to the FAIR principles for scientific data management. As you know, FAIR is findability, accessibility, interoperability, and reuse of digital assets. So this is our future high-level federating all the zones and projects in one big data farm that will have a global search engine on top. So with that, we come to the end of our presentation. We thank you for giving us this opportunity to briefly explain how iRODS has helped us achieve our goals of seamlessly and automatically ingest, annotate, archive, and analyze the lab image datasets.
Thank you for listening to our presentation, and we can take questions now.
Of course, thank you. This is wonderful. I think it's you've moved quite a bit in the last year, and it's great to see the performance information as well. That's something that's always a bit hidden, and so I appreciate you guys being willing to talk about that, in public. It's
Sure. Yeah.
very helpful. I think there were, let's see. So we did have a question about the DynamoDB cache, and I tried to answer it because I think I knew the answer.
Yes.
Did it detect and reflect any removals in the system? And I think the idea is that it doesn't matter because it's just search results again.
Yes, it's just listing, search results, yeah.
So does that mean that the cron job clears out the DynamoDB each time as well? Does it?
No, it just overwrites. It just overwrites. Okay,
so you don't have to worry about stale information.
No.
Because of the nature of the information itself.
Exactly, yeah.
Okay. Very good. I think, so I didn't know if Mike Conway had a question. He had asked, are you following GA4GH distributed analysis? Do you know GA4GH?
No, that's new to me, no, but I'm pretty sure we are not using that.
It's all about repository services and cloud workflows, things like that. So in a standardized way, so that if you were sharing with others, that would be the way in. But it seems like it would just be another arrow on your kind of sharing with others slide. When you publish to what you said, vendors, that could be another place where that could happen.
Mm-hmm. Okay.
We do have a question from Sarah. She asked, have you integrated Amero as one of your tools? Do you know Amero?
No, I don't know that either.
Yeah. So I think, Sarah, the answer might be yes, but I don't know that Radha and Dima would have visibility into that. That would be one of those tools that would be, downstream from the work that's being described here. I would be interested to find out if it was being used inside of BMS. That's an interesting question, because we are working on a possible integration with iRODS directly, kind of in the microscopy world, in the open anyway. So if BMS was at the table, that would be wonderful. I'll figure out. I'll poke around and see if I can figure out the answer to that question.
Sure.
And then Mike says, he's talking more about the GA4GH, just how to think about iRODS in cloud environments in general, because I think BMS is the only presenter in the last couple of years who has been all cloud. Most people still have on-premise installations and are dealing either with the spanning into cloud or the move forward. And you guys have been, I think, Amazon, if not Amazon only, Amazon most.
Most of it is Amazon. We're trying to move towards the GCP and Azure too, but this particular iRODS environment is completely on Amazon.
That's right. Very good. Thank you both. It's good to see you. And,
thank you. Our pleasure.
Thank you.
Probably talk to you again after I take a nap or two.
Thank you. Thank you all.
Thanks.